Good morning, everybody. Myself, Appani Jeratnautam. Today, let's see about Nand Tetris Project 3. In the Project 1, we have seen about the implementation of basic gates and basic chips used in the hack computer. In the Project 2, we have seen about combinational logic and we built various chips like half adder, full adder of 16-bit, a incrementer, and a ALU. And we started from a NAND gate. We built and came into the abstraction. And after that, we started building chips. So we are in this position. So we are in this abstraction level. So from the NAND gates till the abstraction level comes to the project 3. In the project 3, let's learn about memory. Memory. The definition of memory is the faculty of the brain by which data or information is encoded, stored, and retrieved when needed. It is a retention of information over time for the purpose of influencing future action. Memory is time-based. Time-based in the sense we should know about the memory which is previously kept and after kept. So in this way, memory is time-based. The basic abstractions of memory are first the loading a value or second storing a value. That means from memory, we keep memory data into the memory, or we can take data from the memory. So in this way, these are the basic abstractions. The next basic unit, which helps to store memory, is data flip-flop. And the higher memories can be built from the combination of smaller memories. And smaller memories can be built with data flip-flops. So, as discussed in the previous slide, the first step is the data flip-flop. It can be used with a modification with a mouse and be built into a 1-bit register. And different 1-bit registers can be made into multi-bit registers, and combination of multi-bit registers can get into a RAM. And to build this memory hierarchy, we must know how to represent the time, having a clock, registers, RAM, and other counters. Represent the time. So if you have a NOT gate in this example, this is the clock cycle. Each clock cycle, this is the first clock cycle. So in each clock cycle, we can have half off time and a half on time. In this way, if we give input as 1, as this is a NOT gate, we get the opposite output. So we get the 0 as the output. And in the next clock cycle, if we get 1, if we give input as 0 and we get output as 1. And the arrow of time is continuous, and this is the discrete input. We can track changes from each clock cycle to the other clock cycle. Registers. To build a memory storage, we must have the previous information to retrieve the data and update the data. Like if you want to retrieve the data of the previous thing, we should bring it out from the registers. So in this case, combinational logic can't be helpful because combinational logic acts as a function. It's an immediate action. So we come to the sequential logic. It depends upon the previous inputs and also the present inputs. Sometimes the present inputs can be altered. So we can maintain stages and we can store the memory. Thus, registers use this sequential logic to store the memory. We can find plenty of registers in the memory and a very few registers in the CPU. In the next slide, we can see the computer architecture. So in the registers in the computer architecture, this is the input and here we get the output. And this is the computer architecture. First part which interacts with the input is memory, and a CPU it consists of ALU and also a few registers as discussed earlier. So memory and CPU are interconnected and they communicate with each other. And in memory, we can find many registers, and in CPU, we can find a little bit of registers. The RAM. RAM stands for random access memory. This part, the first part after the input is called as the RAM. It's the memory unit. And in the hack computer built in this project, the RAM's main memory is to store RAM's main aim is to store memory. So the behavior of hack RAM is this is the load. So if you load 0, the RAM maintains the same state. Like whatever the data is been present in the previous state will be the same. And if the load is 1, if the load we kept is 1, and if the input value has been changed, then the loaded value will be emitted from the output from the next clock cycle until the next load. Like if the input value is changed, then after that clock cycle, the output will be changed. So note point is only one RAM is selected and all other register on in the RAM, only one register is selected. All other registers are not affected. The triangle, which is in the bottom part, it determines the clock. the cycle which was shown in the earlier counter. So in memory, this memory consists of RAM, and in CPU there is a part called counter. It is found in this registers, and the counter's task is to uh, count the program instruction count. Like if you have a particular instruction which is brought from the memory, we should increment the program counter value to find the next instruction. So the PC is used to store the address of the instruction that should be fetched and executed in the next. So PC can support three abstractions. First one is reset. That means we should first fetch the first instruction. That means PC should be equal to 0. And then if you want to fetch the next instruction, PC should be incremented by 1, that's PC plus plus. And if you want to go to particular instruction, you should fetch that instruction n, then the PC value should be equal to n. In this way, counter value can be updated. So in the project 3, we can find different chips made here. So first, they gave the basic flip-flop, the data flip-flop, and based on using that, we can make the other chips in this project. We can find bit and register, RAM 8, RAM 64, RAM 512, RAM 4K, RAM 16K, and a program counter. These chips are built in project 3. So first, let's go to the first chip which is made. It's called 1-bit register. As the data flip-flop is the basic thing, to store the memory, we have the marks to see the load value and also the input and the previous value. So if the previous value comes from here and been stored here, based on the load, we get the output from the mux. So we use DFF and the mux again. So this is the HTL code of 1-bit register. And let's go to the hardware simulation and check. And in the project 3, it consists of two types, uh, project A and project 3 of 3A and project 3B. And if you go back to the tools, here we can find hardware simulator. In the hardware simulator, we can load the chip, we can load a bit register and see. So here is the HTL code. These are the internal pins. Out 1, DFF out are the internal pins. And input pins are input and load. As we can see here in the slide, input IN and load are the input, and out is the output pins. And as this a bit register is a clocked one, you get a new icon here, which is tick tock. It will increase the clock cycle. One half cycle for a tick, another half cycle for a tock. So if we load the script, which consists of some test cases, here we can see different test cases made here. So if you start running this, uh, we can find the input is set and output is been formed. There's a difference in output and inputs. Here we can see the change in the internal pins here also. If we go and compare in the compare screen, you can find all outputs are same. So after 9 means the first half cycle and 9 plus is the second half cycle. In this way, clock cycle has been done. And if the load is 0, the output is still the same. And if the load changes to 1, then the output changes based on the input value. So as load is still 0, there is no change in the input. If you go back, if when the load value will be 1, then the input value will be changed. Yeah, here after the input value, it has been changed. In this way, all the test cases up to 109, 106, those 107, those we can find the different test cases. We go back after 1-bit register, we come to 16-bit register. The same process, but the thing is, we are connecting 16 1-bit register in a serial way. Here, this is the W bit register. Here, W is equal to 16, and it stores W bits over the time. 1 bit means it has only one load, and here W bit we have one big load, and each connected to the all different loads, and the serially connected. So first input will go into the second input. Similarly, 16-bit register is made. So we connect 16-bit chips together to form the 16-bit register. If we check the hardware simulation of it, after loading the chip, the input pins is in of 16-bit, So input can be given in 16 bits, and load if we load if we keep as 0, the output is still 0. If we make load as 1, and then we can see the output to be changed in the next clock cycle. Similarly, if we load the script of register, we can find after running the input, you can see the difference in the output screen. The constantly has been changed because of one load, and in the next clock cycle, the data has been changed. Similarly, all test cases can be shown here. Next, if you go to the RAM implementation, RAM consists of two parts, reading and writing. Reading can be done with a mux and writing can be done by a demux. So as left side is the input value, here we can find the demux and load and the address part, and mux is the output part. So we have two inputs here again, input and load. So here input and load and address is a 3-bit address, k bits. So on the base of k, we can get the RAM implementation. Here as the RAM is 8, we can find 2 power 3 is 8. So the address is given 3. 2 power 3 is the address part. So up to 3 bits can be accessed in the RAM 8. And input is 16-bit input. And we get different loads. And left side is a demux and right side is a mux. And all registers are connected in a parallel way. So in this way, this is the HDL code of chip RAM 8, and we can find DMAX in the starting position, and then all the registers connected, 8 registers connected to find to form the RAM 8. And before we go to the RAM 64, we will find the RAM 8 hardware simulation. Okay. So here is the RAM 8 clock simulation. This is the HDL code we can find here, and these are the input pins. All these are registered input values, and these are the load values separate each of the register taken, and this is the output pin. We go into the script RAM 8. After we run, make a bit a mix load, and then this is the address, this is the load, and this is the input value. So after giving the input value, when the load is 1 and in the next clock cycle we input the data, the output has been changed. So in this way we can get the addresses, and here we can observe that not all has been changed, only one will be changed. Like all are independently accessed. So we can access separate register in a separate manner. In this way, load and register can be accessed. And next we go to the RAM 64. The RAM 64, we attach 8 RAM chips, RAM 8 of 8 chips together to form to the RAM 64. So input will be the same input 16. Here address will be increased to 6 because 2 power 6 is 64. So we can access 6 bits of address. And here again we have mux of 8-way and mux of 16-way. And here RAM of 512. And in the RAM of 512, 64 RAM of 8 chips of 64 RAM has been attached to get the RAM 512. Demux again in the 8-way and mux 8-way of 16 bits. So in this way, you can give the output and the address is connected simultaneously. RAM of 4K, the chip will be done by RAM 512 into 8 chips. So here, these are again connected in the parallelly. That means we are recursively adding all the RAM which I previously made to make into bigger components. And the reason of having uh, third project 3 has two different parts because as RAM project A will consist of RAM 8 and RAM 64 only, and RAM 512, 4K and 16K will be found in project 3 because as this is made in the recursive way, the hardware simulator will take so much time to execute that if you keep this in the other position, the built-in chips can be accessed because the hardware simulator is made in such a way that if the name of that chip is not mentioned in that particular folder, it will check into the built-in chips and that chips will be added into the hardware simulator. And these are made with the Java implementation and not by the HDL codes. HDL code will take much time compared to the Java implementation. we go back to the projects of project 3A or 3B, you can find the different chips back here. And in RAM 4K, this is the HDL code. RAM 512 is been attached to 8 times. And demux is at the start place and mux in the 16th place. Similarly for 16, and we attach 4K chips 8 times. And in a similar way, we can come back to the diagram hierarchy. So in all registers are connected in this way. This is the input value, the address, load, and the output. The family of 16-bit RAM chips are like N is 8, so K value is 3. As discussed earlier, 2 power value can be found out for the N value. So if N is 8, K value will be 3. If the N is 64, 2 power 6 is 64, hence K will be 6. And as 512, N is 512, K can be found as 9. As N is 4096 as 4K, the K value can be 12, and RAM 16K, which is of N 16,384, you can find K as 14. This is about the hack RAM. Next, we'll go to program counter. Program counter's main thing is to increment the part and also go to the particular position if mentioned. And if reset is done, then we should get back to the 0 position. So the inputs will be input, load, increment, and reset. Here the output value is output 16. Parts are like if first we need to increment. So input value, the register is given input as input 16-bit, and mux to select whether it want input value or it want to check into 0, or we want to increment 1. And all those parts will be stored in register. 3 muxes for 3 different operations. So if you go back to hardware simulator, and if you want, we can also check through the built-in chips. If you go back to tools, in built-in chips, we can find the RAM 16K. And if you load into the chip, we can find the GUI for RAM 16K. And we can also load the script into it. Go to the project 3B has 16K, and giving the input test case for 16K, we can find the loading parts. Or if you want, you can take inputs. Yes, in this way, if you do like this, and all the inputs can be shown, and here the output values can be shown. And to find the GUI, let's go back and load the built-in chips. The RAM 16K, after loading the chip, we find the GUI here. As input, if you want, we can give some values. This is the decimal format, so I can keep the decimal values. And after loading the part as 1, and the address I want as 15th chip to be done. So this 15th chip can be changed in the next clock cycle. As we loaded into 0, the load part can be found in the first RAM. The next clock cycle we found it has to be changed. Go part to the 11th 111th decimal value. Then we change in the clock, 111 part has been changed. Similarly, everything can be accessed in the 16K. There are up to 16,383 parts to be changed. In this way, it has been checked, and when the load is 1, then only it will be rechecked. Now, if we go back to the program counter, let's load the program counter. If you do the built-in chips, we can find the GUI here. This is the PC. Okay, this is the program counter. Here we can find the GUI. If we need to give input as 1, 2, 3, and we need to load the value, and then we need to increment. Then if you do the clock cycle, in the next clock cycle, we found the PCs to be increased. And if we do the load as 0 and increment as 0, in the next clock cycle, it will remain the same. And if we increment to 1 again, and if you do increment as 0, it will not change. And if you do increment as 1, still the PC will be same because load has been not given. We press reset is equal to 1, then the PC value will be made into 0 in the next clock cycle. As we made load into rows load as 1 and reset is equal to 1, then in the next clock cycle, we can find reset to be done. The next clock cycle, PC value has been changed to 0. And if we keep load value as 1 and increment as 1 and reset to be made 0, and the input value to be changed to 0 again. Now, after making another next clock cycle, we find the same value has been kept. And then if we take load is equal to 0, and then we can see increment has been done 1, 2, 3, and constantly after each clock cycle, we can find program counter to be executed in this way. So we come to the end of the project 3. Thank you.